Hello. How's everybody doing? Why don't you say hello in the chat so I can see who's here. And then in a few minutes we could get started. Oh, one upvote. It's only been 15 seconds. Whoever did that, they know I get on my good side. Navik, Jax, good to see you all. 666 Biocane 666. Hello from the US. Glad to have some Italian viewers today. Inman, good to see you. Jonathan and Max, welcome. Grace and Will, hola. Everybody's class is going good so far? Limited amount of trouble with the technology, hopefully? All right, well, it's 10 o'clock, so we could get started. So if anybody has their coffee and would like to join in the simultaneous sip, I got to do it all slow now, just in case it gets choppy at some points. I don't want to mess up the simultaneous sip. So if anybody wants to join in the simultaneous sip, do so now. And so you know the drill. If you did the sip, maybe write the word sip in the comments or do whatever you want to do. Just, get the hype going in the chat. Yes, 2 sips in one day, believe it or not. Austin looks like he was the first on the sip train today. That's great. Okay. Good morning, Ioannis. Good to see you. All right, so the plan for today is, okay, so we ended class yesterday with this example, and I sent you the link to a video that I made last semester. The content is right, okay? Maybe the quality was a little boring, but I'm learning, right? You want to see growth. So take a look at that, and if you have questions, so we could talk about it during office hours in terms of that curve sketching. But that's a good question because it has both types of critical numbers, right? It had horizontal tangents and it also had like the vertical tangents. So it was a good question. But today we're going to talk about section 3.4. Which is limits at infinity. Oh, I'm out of the, let me fix this. Okay. Limits at infinity. Also known as horizontal asymptotes. Okay, so before we get to doing a problem, I'll just write a few sentences about what exactly we're going to do in this section. It's all going to tie into our big goal of curve sketching by hand. Okay, so in this section, we let x become arbitrarily large. and we see what happens to the y value. So we're going to let it go maybe towards positive infinity or towards negative infinity, and we're going to see what happens to the y value when we let x go to those large numbers. And we call this the end behavior. It's because it's like the end of our graph. Okay, so we had a choice, or I had a choice to do the formal definition, which involved epsilons and deltas, or just kind of the the less formal, the informal definition of the limit. And I'm going to go with the informal, just because we have kind of the online setup, and it's the epsilons and deltas were tough in person. They would be even tougher online. So let's define what it means to take a limit to infinity, and then sketch some pictures and look at an example. So we'll let f be a function defined on some interval a to infinity. Okay, so it's the value of x could get as large as possible, is what this is saying. Then the limit as x goes to infinity of f of x equals L means that as our x values get really large, our y values get really close to the number L. So the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. Okay, so that's what it means to have, and it's going to be, hopefully it's more clear once we have a picture. But yeah, so what it's saying is, as our x value gets large, our y value approaches some number, which we denote by L in this case. So for example, maybe we'll have 3 examples here. Say L is this dotted line. Maybe you start above the value and go below, and then you eventually hug the line. You know, as our x value gets larger and larger, our y value is getting closer and closer to L. Maybe you start above and you never cross it. And that's fine. And then the last example is, well, maybe you always cross it. You just bounce up and down over and over again. But eventually it kind of converges to the value L. Okay, so in all of these cases, the limit as x goes to infinity of our function goes to L. And we could make a similar definition for what it means for the limit as x goes to negative infinity to equal L. All we're going to do is just switch. We're going to flip our graph, and everything will go towards the negative infinity. Okay, so we don't have to write out the formal or the informal definition for that. We'll just do it by a picture. So another example, and I'll get out of the light. So here, notice it says negative infinity instead of infinity. And I'll just do the same pictures, but just flipped. Okay, and it's possible that a function goes to some value towards positive infinity and to a different number when you go to negative infinity. And we'll see plenty of examples of this. So before we get to like an actual example where we're going to have to do some computation, let's define what this is. We call this dashed line, and I'm sure, can you give me a yes or no in the comments? Have you heard the term horizontal asymptote before? Probably in your pre-calc or algebra 2 class. But what we're dealing with here is just a more general sense of the horizontal asymptotes that you saw in when you looked at rational functions for the first time in, I'm assuming, algebra 2 or pre-calc. Okay, so a few of you have heard this term before. So it's going to be the same sort of idea as what you saw in high school, just we're going to describe it in terms of limits. Right? Remember when we defined the vertical asymptote, we also defined it in terms of limits, and it captured a little bit more the idea than maybe what you heard in high school. So we're going to define a horizontal asymptote. So the line y equals L is called a horizontal asymptote. Of the curve y equals f of x if either the limit as x goes to positive infinity of f of x equals L, or the limit as x goes to negative infinity of f of x equals L. Word IDK if you're not sure. How many possible horizontal asymptotes could a function or could a graph have? What are the possible numbers of horizontal asymptotes a function can have? So put your guess in the comments, in the chat, and then we could talk about that. Max says 2. That's true. You could have 2. Are there any other values? 2. A lot of 2s. Okay. It could have up to 2. Yeah, that's the answer I was looking for, Jax. Yeah, it could have 0, right? If these limits don't exist. Imagine if our graph just went off to infinity or negative infinity, then it wouldn't have a horizontal asymptote. And also, if our function just wasn't defined for large values or small values, it also wouldn't have a horizontal asymptote there. Yeah, so up to 2. It could have 0, it could have 1, and it could have 2. So let's do a sketch. So for example, if you have a curve like this, maybe this is the line y equals 3. And this is the line y equals -3. In this example, the limit as x goes to -infinity of our function is 3. And the limit as x goes to positive infinity of our function is -3. So we have 2 horizontal asymptotes. So Jax asks, why can you cross a horizontal asymptote but not a vertical one? I will answer that. Let me just write this down. Yeah, so why can you cross a horizontal asymptote but not a vertical one? Well, my answer to you is you can't cross a vertical asymptote. Take a look at our notes in the notes of what it means to have a vertical asymptote. It means that the limit from one side goes up to infinity or negative infinity. Remember we had, and I'll maybe sketch an example of this. We had an example where our limit went up to infinity from one side, and then from the other side, it starts on the vertical asymptote and maybe goes out this way. I mean, technically, it's not crossing it. But yeah, our requirement, and this is where, okay, sorry if there's any high school math teachers in the chat, but I'm going to say it. This is where maybe we're a little bit misled with what we're taught in high school. Because asymptotes just really talk about what happens to the curve and its end behavior. It's not about crossing or of those sorts of things. Yeah, so here we'd have a vertical asymptote, but we still are defined on it. Yeah, it's just, so for a horizontal asymptote, it's really just asking you, what does our function do at infinity? What does our function do at negative infinity? It doesn't matter if we cross it 1,000 times. It's just asking what happens to our function as we get to infinity or negative infinity. Okay. So we'll start with a theorem, and then we'll finally get to an example where you could try to work one of these out on your own. In fact, we have a lot of examples. Yeah, so let's state this theorem, and then we'll do a few more examples. Like we'll basically spend the next 30 minutes working on examples. Okay, so if we have some rational number here, maybe this detail's not terribly important, but the point is we have a positive rational number, then the limit as x goes to infinity of 1 over x to the r is equal to 0. Okay, and so what this is saying is you have 1 over a really large number raised to any positive power, it's still going to be a really large number in the denominator. And so when we do 1 divided by that number, it's going to tend to 0. Okay? And so we could use this fact to look at an example. I guess we should state one more part of this theorem. So if x to the r is defined, then the limit as x goes to negative infinity of 1 over x to the r also equals 0. Okay, so when you do the negative infinity, when you go to negative infinity, you just got to make sure that we're allowed to actually perform this operation of plugging in large negative numbers. But if you can, then this limit also goes to 0. So just this little subtlety here is just make sure we don't take the square root of negatives. Okay, so before we get to the example, are there any questions, or are we good? Any feedback in the chat would be appreciated. Absolute silence in the chat. That is fine. Just like class as usual. Okay. So let's take a look at an example. So the example says evaluate the following limit. And it's the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So I don't want you to just give me the answer. Can somebody maybe put in a sentence or a half a sentence of how would you actually go about doing this? Do we have any ideas of how we could use this theorem to help us solve this problem? Yeah, you're on the right track, Jax. Divide by the, oh, sorry, you are exactly right. Yeah, so what we want to do is we don't know how to evaluate the limit when we have like infinity in the numerator and infinity in the denominator. But what we could do is divide each term by the highest x to the highest power that appears in the denominator. And then we could try to evaluate the limit. And we could use this theorem to show that most of the terms will go to 0. And what's left over will be our answer. Okay, so I'll kind of write out those steps so we have it in words in case this video is choppy and you can't really hear me. So we're going to multiply the numerator and denominator by 1 over x to the r, where r is the largest power of x in the denominator. Okay, so what we would get would look like this. Okay, and now we could multiply all this through. And we get this. And so what is the value of this limit, which is exactly the same as what we started with, just rewritten. You don't have to explain your answer. You could just type in an answer and I'll explain it. Yeah, Inman, you're right. It's 3/5. Term goes to 0, this term goes to 0, this term goes to 0, and this term goes to 0. So our numerator would be 3 plus 0 plus 0, and our denominator would be 5 plus 0 plus 0. That's just 3/5. Okay? And if you're like me, or if your high school teacher was like my high school teacher, you had a kind of a method for checking the horizontal asymptotes for rational functions, which was if their powers were the same, then you just look at the coefficient. You just look at the leading coefficients. So that's a good way to check your answer if you remember that trick from high school. But unfortunately, we're going to look at harder problems than you looked at when you were in high school. So we're going to have to come up with some new tricks. So before we move on to the next example, just can I get a little feedback? Are we good, or should we slow down? So say, type go on if you want us to go on, or stop if you want us to slow down. Or good is fine also. Okay, good. So it seems like we're so far so good. I will ask this same question after the next example, and I expect this next one will be a little bit harder. So don't be embarrassed if you want us to slow down, because this next one's tougher. Okay. So it's find all horizontal and vertical asymptotes of f of x equals the square root of 2x squared plus 1 over 3x minus 5. Okay, so before we do the horizontal, let's start with the vertical asymptote. How do we find the vertical asymptote? Or if you want to type in your answer for where a vertical asymptote is, I could kind of explain the details. Yes, Rena, exactly. We want to set the denominator equal to 0 and solve, and then just make sure it doesn't cancel out when we plug it into the numerator. Yeah, so now just to double check, we should take the limit as x goes to 5/3 of our function, and just make sure that this goes to infinity. Another way to do that is just you could plug in 5/3 in for x and just make sure it's not 0 in the numerator, and it's not. So it's the square root of 59ths plus 1 over 0. Okay, so we have our vertical asymptote is x equals 5/3. How do we find the horizontal asymptotes? Okay, well, maybe we don't have an idea. That's okay. So remember, to find the horizontal asymptotes, we want to take the limit as x goes to infinity of our function, and we want to take the limit as x goes to negative infinity of our function. And those values, whatever we get, will be our horizontal asymptotes. Okay, and so the way we're going to solve this or evaluate this limit is we'll do the same thing. Multiply the numerator and denominator by 1 over x to the r, where r is the largest power of x in the denominator. The largest power of x in the denominator is 1. Okay? So far, so good? Okay, and now our denominator is in good shape. We're ready to just plug in infinity and we'd get 3. But our numerator is still a little bit of a disaster. So this is where I wish we were in person because it'd be easier to ask for ideas. I'll just explain. I won't wait for input. What we could do here, so we have a square root in our numerator. We could replace x. So we're going to use this fact, and I'll write it in red. So since x is positive, x is equal to the square root of x squared. If x was negative, then it would be the negative square root, right? Because the square root is always, we pick it to be the positive version. And so we're going to replace x with the square root of x squared, and then we can combine this into one big square root. Okay, and please put in a comment or put something into the chat if you want me to go over something again, or if my explanation is choppy, or you just want me to say it again, because this is an important concept here. You know, this step going from here to here is an important one. So then we can take this square root of x and break it apart into 2 separate fractions. So we get a 2 and a plus 1 over x squared. Sorry, we'll take the x squared, not the square root. So we have a square root of 2 plus 1 over x squared inside of our square root. But we know how to evaluate this limit, right? Because that term will go to 0. And then we also know how to evaluate the bottom limit. So this works out to be square root of 2 over 3. Okay, and now that's when we take the limit as x goes to positive infinity. We also have to take the limit as x goes to negative infinity. As in, we'll multiply the numerator and denominator by 1 over the highest power of x. We get this. And now here's where we'll write the fact in red. Now we're taking x to be a very large negative number. So since x is negative, x is equal to negative the square root of x squared. Okay, this is very important. What I wrote in red will be showing up a lot, and we'll start class tomorrow with an example that will take advantage of this fact again. So when we're replacing x with the square root of x squared, it comes with a plus or minus depending on if we're taking the limit to positive infinity or negative infinity. But now that we have this fact, we could replace x with negative the square root of x squared. And now the arithmetic follows exactly the same. Okay, so while I write out kind of our final answers here, let me know if you have any questions, because there is a little bit of a delay between when you submit it and by the time I see it. So type in any questions. I'll get to those. So just to recap, so our vertical asymptotes was x equals 5/3. And our horizontal asymptotes was y equals square root of 2 over 3, and y equals negative square root of 2 over 3. Okay, so as our x value gets large and positive, our y value tends to square root of 2 over 3. Similarly, when x gets large and negative, it goes to negative square root of 2 over 3. Nicole, more often than not, yes. But if, for instance, we were adding together two, if we didn't just have, where did we start with? If we didn't just have this rational expression to start with, and maybe we added some number at the end, like a +1, then it wouldn't work out like that. So yeah, you should go through and actually check the whole, work out the whole process. But when you have just a rational expression without anything added to it, then you're right. It will just be plus or minus. Why did the 3 minus 5 turn into 3 minus 5 over x? If you're talking about going from here to here, we divided each term by x to the first. We multiplied the denominator by 1 over x raised to its highest power in the denominator. Okay, yeah, we should be careful about that. It might go to negative infinity, but the point is, so the question was, how do we know that the vertical asymptote goes to infinity as opposed to negative infinity? We don't really care. We just needed to go to one of them. So we knew it because it was a number divided by 0. And so it was a positive number divided by 0, so it's going to go off to, well, yeah, really this should just be does not exist. Or plus or minus, depending on which side it comes from. So yeah, we do have to be careful about this vertical asymptote part, determining if the limit goes up to positive infinity or negative infinity. But if you look back at how we found vertical asymptotes in the first place, it just, we needed it to go off to one of those infinities. So we maybe left out some details there, but that's not terribly important. Okay, let me write out one more example. We're not going to have time to complete it. But this is what I want you to think about tonight. And it's okay if you can't quite figure out how to do it, because it's hard. we want to compute the square root, or the limit as x goes to infinity of the square root of x squared plus 1 minus x. So if we just tried to evaluate this limit by like plugging in infinity, we would get infinity minus infinity, which is meaningless. Okay, so we will have to be a little bit creative here with how we're going to solve this. So does anybody want to just maybe put a guess in the comments of what we might do to manipulate this function so we could solve it? I notice there's like a square root here. Think of how we evaluated like the limit definition of derivatives with square roots. We'll probably use the same technique. And if you have no clue, maybe just type the word no clue or something like that. I don't know. Jax, you're on fire today. You're right. That's a good idea. So what we're going to do is we'll end up multiplying by the conjugate to see if that helps us out at all. And then maybe it's going to simplify to a question like we have here. So yeah, so that's the big idea. Obviously, it's going to take more than the 4 minutes that we have left of class. So try this tonight. We'll start class with this tomorrow. But other than that, I'll answer questions in the chat if anybody has any. But I'm done with material today. Make sure you hit the like button on your way out. It helps the channel. Oh, it's so bad. Turner, we're waiting for the 1,000 subscriber special. 500, it went by like nothing. We're looking for 1,000, and I think we'll get there sooner or later. This online coronavirus thing is really helping the channel grow. All right, I'll give about 30 more seconds for questions, and if there's no questions, I'll end the stream and see you later. Just call it CV. Yeah, it's the CV, the CV bump. Okay, bye-bye.